Welcome to Code Together, an interview series exploring the possibilities of cross-architecture development with those at the forefront. Scientific visualization is providing new insights in healthcare and advancing medical research in ways that we couldn't imagine a decade ago. It's an evolving and promising field where extracting visualizations from very large data sets can improve analysis, diagnosis, and patient outcomes while reducing costs. Today, we'll hear from two guests who are working in scientific visualization in different ways.
Here at University of Chicago, my role was to help researchers across different departments, hospital, public policy, chemistry, and so on. I remember one story when the surgery department contacted me and brought me a large data set of this billion simulated Willi cells coming from supercomputing simulation. So they were trying to basically study intestinal immune diseases. They are in the intestine. And these diseases affect like 1 in 100 people worldwide. And I got the data. I was trying different tools that existed to visualize. I was going into Python libraries and OpenCV and OpenGL. I heard about this hackathon that was organized at the Texas Advanced Computing Center on Visualization. And there's where I met this amazing community. I met Jim Jefferson from Intel, Paul Navratil from Tech. So when I arrived there with my data, it was a timing because they were testing their new developed tool. And it was like magic, plug and play. I could see the visualization of my billion cells in multiple colors, different orientations. Now also having a lot of visual cells to visualize, I had a very big screen. We call it wall of knowledge. So when I brought the Willi cells and visualized it in the screen, it was a different experience to be able to rotate and zoom in and see the difference in the patterns. Amazing.
So visualization has really changed your research dramatically with the big data sets and being able to visualize them and manipulate them on this giant wall of knowledge. That is truly amazing. So I'm curious, how has COVID impacted your work and not being able to stand in front of that screen and do your research and really understand the depths of the medical processes you're looking at?
Last days before COVID, when I was there, we were just able to reproduce on the screen this impressive visualization. It's a massive star, 100,000 times bigger than the sun. Using ParaView, that visualization was amazing. So I was just getting started being super exciting on using the wall when pandemic came. So I couldn't go anymore on the laboratory. I transitioned more into projects that are less into visualization, more computer vision, deep learning. So one of the projects I'm working, and I love working this project, it's impressive. It's really measuring structural inequality in children's books. And of course, I'm interested in the images of the children's books. And I like to call this the invisible monster, just to relate to children. And this invisible monster basically is the discrimination that is built in social structures and institutions that don't really notice. So we are trying to understand how the images in this book really influence what children think that's possible for not only for them, but also for the others. So for example, if a man never sees a woman as a president, then he might think that this is not even possible to vote for a woman as a president because he cannot envision this possibility.
It was great that you were able to almost like reinvent yourself and take on some new projects still with visualizing and imagery in the context of diversity. Has COVID led you to, research directly related to COVID itself?
I started supporting a team in the section of pulmonary and critical care medicine at U Chicago. It was in a project that uses artificial intelligence to predict the maximal oxygen support that will be needed for the COVID-19 patients based on their chest x-rays and their clinical data. At the beginning of the pandemic, it was a crisis on even hospital beds, but also ICU beds. And not everyone was lucky to, in some countries, to have the really good care that they needed when they got infected with COVID. So this team were some of the pioneers in placing these less critical patients into, we call them oxygenated helmets. So instead of pursuing the more clinically involved options of using ventilators, which requires going in intubation and taking a patient to ICU for a certain number of days, the team look at if the level of oxygenation is not needed as much, then they put the patient in helmet.
What a novel idea to be able to give acute care and advance notification to patients who may need intensive care, and there's minimal beds. And what a great research. Let's circle back a little bit more on the visualization. And, you mentioned big data sizes and clusters. Can you share a bit more insight on your computing infrastructure?
So it's very exciting because our cluster is named Midway, but this year we launched Midway 3, which is a high-performance computing cluster of about 2020 nodes and over 10,000 cores. Now, together with the Midway 2, we make around 40,000 cores. But what's special about Midway 3 and so excited because it's really dedicated for AI extensive jobs and deep learning. It's the first time we built a system that is both Intel and AMD processors. And also we have NVIDIA A100, V100, RTX 6000 GPU capabilities nowadays. The difference between our previous cluster compared to this one, I'm doing deep learning. I can really see the performance going super up.
How does performance impact your research, like the performance of this infrastructure?
For example, for the Midway 3, all my projects include deep learning. So anytime I go and train a model, now instead of going and waiting for the training to happen in 2 days, it might happen in several hours. Also, we are really excited because Midway 3 this year was used to, I don't know if you know, the University of Chicago, a team there was the first to generate a computational model of the COVID virus. And I know they use Midway and Frontera system attack and other systems, but it's interesting to have this computational power to generate models and looking forward into doing maybe in situ visualization and looking at how the model looks like while the simulation is generated.
So then on top of the infrastructure, we've got this layer of software. And you had mentioned, the oneAPI rendering toolkit. How do you use the ray tracing APIs in your research?
So mostly these days, we are looking in the medical field. I'm really interested on, for example, simulating how cancer lesions might develop over time or how the tumor is growing in certain areas of the body. And using imaging, we know the location of the tumor, but also using simulation and basically knowing the mechanical process of the cancer growth, we can look at how the cancer is spreading in the surrounding tissues. So oneAPI and the rendering toolkit would be really interesting to have a visualization of these structures and segmenting them and watch over time by simulating how they could develop in what surrounding regions, in what shapes and forms.
So in your simulation, do you generate a whole lot of data and look at it at the back end, or do you use in situ type simulation where real time you're observing the data as it's being generated?
how I like to describe in situ to people that do not know what's in situ is, imagine I'm buying a car and I give to the manufacturer all the specification, color, what speed, what's the noise, what music, system, everything. And they come back to me 6 months later and say, here's your car, bye. And it's not like that. I would like to go maybe and visit them every week and check on the progress and adjust little parameters. More and more we transition into having simulation and generating visualizations real time as the simulation is moving on and it's advancing. So we can check on results every time and we can go back and change parameters if we see that the simulation goes in the directions we don't want to. Right now, majority of our in situ visualizations, we use ParaView and Catalyst for processing them.
So what I do in the advanced rendering and visualization architecture team is those components that you know and love out in open source, be it Intel, Embry, Osprey, Open Volume Kernel Library, Osprey Studio, Open Image Denoise. I take those components and add a little layer of glue on it to format them into the oneAPI rendering toolkit bundle. And what that all means is you get the same great APIs, no change. I pulled the source code from the GitHub releases and I distribute easy to use binaries in a toolkit bundle. And you will have this toolkit install on your Windows machine, on your Linux workstation, and the installation will download everything you need to run those libraries. And that's the ease of use that we've brought to the user community through the oneAPI rendering toolkit. So you can make your development real streamlined, make updates of the components within your applications very easy at the click of a button.
I think it's all into generating real-time visualizations and being able to get immersive experiences. And we are working with the simulation center sometimes where they have simulations to cut into tissues and see the development of certain tumors. But also on the other note, I couldn't stop being so impressed by Donna's mention of how the Osprey library and the oneAPI framework and toolkit are really easy to install and reproduce and are open source. I wish the code in the academia is as easy to install and reproduce. So this year, maybe because I had time to sit down more and be with the code, I got really into advocating for bringing more industry resources and best practices for writing code and creating products to academic area. So having reproducibility and great documentation as the Osprey library has and collaborating.
So I am thinking big, and big. I'm thinking, big data getting even bigger, big compute power on HPC clusters, big storage capability, factoring in the powerful Optane memory that can drop right into your machines and expand your memory footprint into the terabytes.
Thank you so much. Let's continue the conversation at oneapi.com.